Continue straight from previous video where we calculate the design bending moment at the midspan, we calculate design bending moment at discontinuous edge, and we calculate the design bending moment at continuous edge. Now our intention is to find these reinforcements. What is this reinforcement in the red color? That is the primary reinforcement, that is the bottom of the slab. That's we want to find the intention. What is the area of that reinforcement? So now in that case we're going to make a 1 meter wide strip. So we can, let's say, draw up this strip here. Let me draw with the black pen. So let's take a 1 meter wide strip, 1 meter wide strip, and we're going to work through this 1 meter wide strip, and we will see what area required for this 1 meter wide strip. Now couple of notations. We are working with primary reinforcement that is provided at the bottom tension side of the slab, that is on the short spans. So if you can think of the beam, the slab here, that we're going to along the short span, so that is red one. At the midspan, so we are talking about at the midspan first. We want to apply it here, midspan. In the x directions, we call it in the x directions. It has bottom reinforcement. It is also called sagging because the beam generally sag. I can show it to you with the rulers if I can find the rulers here. So the beam generally at the midspan will have a sagging. So it will have this sagging, and this is hogging. So this beam will sag under this loading condition. So that slab will sag, and it is positive bending. So this one here at the positive bending. So basically we are working with this mx star plus. What reinforcement do you require for this mx star? So the capacity of the slab for 1 meter wide strip should be greater than m star. What is m star? M star is, we calculated this positive bending which is coming from bending moment diagram, that is 14 kilonewton meters for this region. So let's say this is 14 kilonewton meters positive bending moment. Capacity factor, capacity reduction factor 5 is 0.85. we can take it here. We are designing for under reinforced. Consider this one as a beam, okay, because if you have 1 meter wide strip, then it's not slab but it is considered as a beam. So in that case, bending without axial tension and compression, and slab also bend also have a bending phenomenon. So we can take 0.85 considering under reinforced assumptions. So we take 5 equal to 0.185. Now if you remember this kind of stress block coming from the beam designs, where you have a tension phase, compression phase, you have this compression stress and you have tension stress in the reinforcement, and you have this depth d from the reinforcement to the top of the compression edge, and this is the force in the compressions. And if you, let's say, you have distance a for this compression stress, distance d for this tension stress, you would have this lever arm meaning that distance from the steel force to the compression force, that is the lever arm. Now I need to have some notes for this lever arm. We don't want to go through this long process where we're going to find the neutral axis depth and so on, but there is a very good assumptions that we use that is accurate within plus or minus 10%. So when mu act in the under reinforced beam, this 1 meter strip is the beam. The neutral axis depth is high in the section. So meaning that this neutral axis depth is somewhere sitting in the high, not in this zone. It should be somewhere very close to the top of this compression edge, that is under reinforced, and that's how we design, because that is a ductile failure. We don't want to have a brittle failure. So we have a neutral axis sitting high in the beam. How high? We're going to discuss it. And the neutral axis lever arm Z is not much smaller than the effective depth of this one. So this lever arm distance is not, it is less than d, you can see, but it's not too small. We don't have lever arm like this. The lever arm like this would be very it's wrong, okay. So you don't want to have very small lever arm. We want to have this lever arm which is not too small. It is less but not too less than the effective depth of the reinforcing stem. So the lever arm generally less than effective depth, but it's not too less. How much? I'm going to discuss it. Typically the depth of the neutral axis dn may be taken as, so how much depth? So let's say you have depth of the neutral axis. How can you estimate this depth of the neutral axis for under reinforced? It is typically falls between 0.15 to 0.3 d. So this is the range that we can take it. although the some beam will have very high, but this will have a brittle failures, and we're not going to falls in this category. Generally we design it between the range of 0.50. So this neutral axis would be have a range of 0.15 to 0.30 D typically. So if you have 100 millimeter D, this generally 15 millimeter to 30 millimeters. Okay, that is 15 to 30%. So in that case, if you want to have a lever arm Z, typically we take it 0.15 D. Okay, as I mentioned, we don't want to take too small lever arm, we want to have a reasonable. So if you have a this D 100 millimeters, this lever arm would be 85 millimeters. Okay, that's what I'm talking about. I don't want to make it 10 millimeter lever arms, so I'm taking 100 because that is reasonably it's mathematically easy to explain. Otherwise we would have real numbers. So mu is this is a pure bending, so you can take the moment about any point. So let's take the moment about this point, and anti-clockwise is positive. So the moment, if you have, let's say, moments going in this direction, so moment equal to AST, which is, let's say, force is equal to stress times area. So this TS equal to force times area times 0.85, that is the force times distance, perpendicular distance, this lever arm 0.85. so this is the good assumptions. Okay, so these equations you can go and use this equilibrium, and you can find this actual DN value, but that will require mathematically a lot of steps. So we can avoid that steps, and saying that for the slab we can have this approximate value mu is give you the value within plus or minus 10%. So it's a good estimate. Now in this case, once you understand this lever arm story, which is 0.85 D, as I mentioned, we're going to take the moment about this point, pure bending, anti-clockwise is positive. So the force in the tensions times this lever arm, which is basically D take away A by 2, and we discussed lever arm is 0.85 D, it just now. This force is equal to stress time area. Stress in the steel is 500. We have n bar, so in n bar 500, let me find that n bar. There you go. At the start of the standards, we have in the page number 51, you can have this n bar. I think somewhere ductility n bar we have 500 megapascals. That's given here. So therefore we take it 500 megapascals, and we at the start we assume that class n. Let me find that. At the start we assume that N12 class bars. Generally we use N12 and N12 and 16 bars in the slabs. So for that N we have 500 megapascals. Area of the steels, we need to find how much area of the steel. Please note this is per meters, times 0.85 D times 14 kilonewton meters times by 1000 to convert into Newton times by 1000 against to convert into Newton millimeters. That's what we are working on. This D, we calculated this small d. Please note this is not the depth of the slab, but that is the small d here. That based on this 150 millimeters, we calculate small d 119 millimeters in the previous videos. So we have 119. If you simplify this, bring across this, divide by this, it will give you 326 millimeters square per meter. So that's the area required at the bottom of the slab per meter width for the sagging region at the mid spans. In the next video, we're going to look at the minimum reinforcement required using the AS3600. Thank you.